a type of protein also found in human hair. The egg white, or the albumin, which cushions the yolk, is composed of 10% protein and 90% water. As food, egg whites are useful as binders for baking. And because these are high in collagen, a protein that promotes skin elasticity, egg whites are also used to make face masks. And finally, the egg's yellowish center, the yolk. It makes up 31% of the entire egg weight and contains plenty of vitamins and minerals. The color of the yolk is dependent on the hen's diet. Eggs from pasture-raised hens are said to have more omega-3 and less cholesterol due to its consumption of natural feed.
Welcome to another beautiful Tuesday afternoon. You are watching Tenfold Live, and I am Tobile. I want to send a big shout out to Liberty. Thank you so much for sponsoring the show once again. Thank you so much for giving us the opportunity, as well as to help the class of 2021. I know most of you guys actually wrote paper 2 yesterday, so hopefully all the rest of the exams are going all well. And another thing, I want grade 12s, if you haven't downloaded the Tenfold Education app, please do so ASAP. Hopefully you've seen how difficult the prelims were and where you actually need help and so forth. And the Tenfold app is an app that can actually help you prepare. And if you're wondering what questions we are doing, please do send a hi on the WhatsApp number on the screen, and there we will therefore send you the questions we're doing today. Another platform where we actually are live and active is then on YouTube, and there we are Mindset Learn. So without wasting any more time, in today's show, we're going to be looking at paper number 2 revision once again. So remember now we're looking at the final. So hopefully you guys have seen where you still need help, where your mistakes are and all that stuff, and we're going to help you do that. So the first question that I have is from Lunar Winter, and this is question number 2. And what I like about question number 2 is that it's actually organic chemistry. And remember, grade 12, organic chemistry counts most of paper number 2. So if you're really struggling with naming compounds and how do they actually react and knowing the functional group or the homologous series in which they belong to, then you already have a problem. Remember, when you start with organic chemistry, each and every homologous series and functional group has properties that makes it unique and that makes it so special. So you need to know exactly what's going on as we start. So in today's show, I'm going to show you what the examiner wants, how you need to answer, and how I would actually approach the question. So for question number 2, it says letters A to D in the table below represent 4 organic molecules. So we've got number A. So I'm going to analyze each one and see in which functional group does it actually belong to. So I can already see that this one has a triple bond there and nothing else there. So this must be alkynes with Y and E. I'm looking at B. I can see that there's a carbon attached to a double bond O with 2 carbons on the side. Remember, if the double bond O was on the side, it would have been an aldehyde. But the minute we've got a double bond O in the center, then it is a ketone. How do I know this? Remember, when you start with organic chemistry, you need to know the structural formula of each functional group. So this is where I'm actually getting it from. So I find something that actually makes it unique, and therefore I'm able to answer the question or actually identify it. So here at C, I've got a HO at the end. So in drawing the molecule, remember, if it has an HO, it can either be an aldehyde or it can be an alcohol, but it's not drawn. This is a condensed structure. Then we've got butane. There's no triple bond, nothing, so this is just an alkyne. So 2.1 says, I must use the information in the table to answer the questions that follow. So write down the letter that represents ketone. Now, what most of you guys do is, remember, when the question says you must write the letter, you cannot write me the name. The examiner wants to see if you understand that in all the 4 organic molecules that you're actually given, or compounds, you can actually identify which one is a ketone. So let's go back. With these 4, I remember that a ketone is a C attached to a double bond O with 2 C's on the side. So that will therefore then be letter number B. So ketone will be represented by letter number B. And then 2.1.2, I must now write the structural formula of the functional group of compound number C. What I tend to see most of the time, especially in the marking center, is you guys sometimes get confused if they say a structural formula, a condensed structural formula, and so forth. So remember, when they mean, those words actually have a different meaning. The examiner wants to see if you understand what's actually happening. So we must draw the one for compound number C. So if I had to now draw this, they're just looking for the structural formula of the functional group. Remember, functional group, what makes it unique? Is it an alcohol? Is it an aldehyde? And so forth. So I can see that I've got a C. Just by analyzing this, I've got 2 H's. I'm just going to put a C, an H there and there. This C is also attached to 2 H's there. I've got a C that's only attached to 1 H. So it means, okay, somewhere, somehow there might be a double bond, meaning that this O will then have to be attached to this one. Because remember, you must have 8 lines around it. This only has 2 with 2 hydrogens, and it's bonded there. So I can see that this O that is at the end here will be then attached to this carbon here, which means that this will then be an aldehyde. So they want just the structural formula of the functional group in which it belongs. Therefore, the structural formula of compound C, which is an aldehyde, will be a C, a double bond O, and it is therefore attached to an H. Now, I just want to show you this. If you were to draw it as C double bond O and only leave it like this, that is unfortunately incorrect. Remember, an aldehyde needs to be attached, the O needs to be attached to the carbon at the last end, meaning that if I do this, I can add a C and a C, which makes it a ketone. Then now I'm talking about structural isomers. So make sure when you're drawing the structural formula of an aldehyde, you actually put an H so that this is actually at the end of that molecule. And that is only for 1 mark. Let me just take this one off. Okay, 2.1.3. Now they want the general formula. They want the general formula of the homologous series to which A belongs. Remember, guys, when we do or when we use general formulas, a general formula is a formula that actually kind of guides us to tell us, okay, if we're talking about aldehyde, how many hydrogens do we need to have, how many carbons, and so forth. There's always a ratio of carbon and hydrogen in every single time. So now you need to know the functional, the general formulas off by head. But there's also a trick where you can actually draw a structure and then figure it out. So let's look at what A has. So they want the structural formula for number A. And I can see that number A has got a triple bond there, meaning that there are actually 2 hydrogens that are out of place there. So the structural formula, let me go down all the way here. The structural formula for A will be Cn. Remember, it's a subscript N, CnH2n minus 2. This means that this is therefore, there's a triple bond going on there. And then the last question says, I must give the IUPAC name of a, remember IUPAC is an acronym for something that we use in applied chemistry. So I would also know the definition for IUPAC. I've seen questions where they actually ask you the definition for IUPAC. And so let's give the IUPAC name of compound number A. So I'm going to break it down and then we're going to put it all together. I'm going to do it step by step. Just want to go back before we start so that you know exactly why I'm doing what I'm doing. So the rules for naming organic molecules is, step number 1, we need to find the longest chain. So when you're finding the longest chain, it doesn't really matter which side you start for now. So you find the longest chain, that's step number 1. Step number 2, the double bond, the triple bond must always take the smallest number. That's where we start coming in, whether we start naming from the left or to the right and so forth. So the double bond or the triple bond must always take the lowest number. Then the next thing, I want you to highlight or make a bubble around all your little kitties on the side chain. Some call it children, some call it side chain. So whatever is not part of the longest chain, right? Your branches. Now with the branches, what most of you guys do, remember you give it a number, right? And it must always be in alphabetical order. Even if the number is the biggest, it must always be in alphabetical order. Another mistake that you do, which is very important when you're using the IUPAC, is the fact that you cannot just use a comma anyway, and you cannot just use a hyphen anyway. You can only use a comma between numbers and a hyphen between a number and a name, right? And remember the name ending for each and every one. So let's tackle this. Step number 1, we must find the longest chain. So I'm going to start here. I'm going to say 1, 2, 3, 4, 5, 6. Let's see another one. If I say 1, 2, 3, 4, 5, 6, that's another chain. Or I can say 1, 2, 3, 4, 5, 6, that's another chain. Let's see if we can find one last one. 1, ooh, you can't see the black. Let me try another color. 1, 2, 3, 4, 5, 6, 7. Aha. So I see that the light yellow, that is there for my longest chain. So I'm going to erase everything else. So now we found our longest chain. How I always teach my children, always use a highlighter with the different, like how I did now. Use a highlighter and find your longest chain. So use a pink or a pink colored pen and you can see your longest chain with the different highlighters. It just makes it much more easier. So there's my longest chain. Now we need to see. If I say, now I need to find my double bond or my triple bond. Let's start with our side chains first. I've got a side chain there, I've got another one there, and I've got another one there. So I've got 2 carbons attached to this one. I've got 1 carbon on this side, and therefore it goes on my longest chain. So let's see, 1, 2, 3, 4. So this is my 4th carbon. I've got 2 carbons, which is ethyl. So 4, 5, 6, and then 7. So let's see. 4, this will be 5. On 5, I've got another side chain, which is only 1 carbon, which is methyl. There's only 1 carbon there. And then my longest chain is 7. And remember, 7 carbons is hept. So that will be hept. And then I've got my double bond. Remember, it must always take the smallest number. So just for argument's sake, I just want to use blue. Had I counted this way, 1, 2, 3, 4, 5, 6, 7. Let me use the yellow. 1, 2, 3, 4, 5, 6, and 7. Can you see this is where my side chain is? Just going to make a dotted line. If I use the blue, then my side chain gets a number 6. If I count in the yellow, then not my side chain, my triple bond gets a number 6. If I use the yellow, then my triple bond gets a number 2. The triple bond or a double bond must always get the smallest number, regardless of what the other side chains are. It must always take the smallest number. So in this case, I'm going to have to count in the yellow because I can see therefore it is then a 2. So what I like doing, I'm going to break everything up and then we're going to put everything back together. Let's just go back. So now I showed you now how I'm going to break it down. So let's start naming. So remember on the 4th carbon, remember a number and a name is separated by a hyphen. On the 4th carbon, I've got 1, which is ethyl, and that is my branch. On the 5th carbon, I've got 2 carbons, which is meth. So this is methyl. My longest chain is hept. However, on the second carbon, I've got a triple bond, which is YNE, which belongs to an alkyne. So now what did I do? I found my longest chain. I gave my longest chain a name. I also found all my side chains. I also figured out in what carbon number is my triple bond going to be. Now, the last final step that we need to do is put everything in alphabetical order. Make sure that we put the correct commas in the correct place as well as the correct hyphens in the correct place. So let's see. I can see that E comes before M. So therefore, I'm going to say it is 4-ethyl. 4-ethyl, 5-methyl. My longest chain is hept. On my second carbon, I've got a triple bond, which is YNE. So therefore, for 3 marks, we're going to have 4-ethyl, 5-methyl, hept, 2YNE. So if an examiner is marking this and you got the hyphens right and you got, let's say, all the numbers right and all that stuff, however, you didn't put in alphabetical order, you still get a chance to actually get 2 out of 3. Because what does the examiner see? The examiner can see that you actually know exactly what's going on. You just forgot to put everything in alphabetical order. But remember, if you do not put a hyphen in the correct place, that actually you do get penalized for that. But in this case, this is how you would have done it. And that is how we do the IUPAC name. So now for number 2.15, this one's only for 2 marks. It says we must also give the IUPAC name that we use in applied chemistry to name compound number B. So let's go to compound number B. This one is pretty easy. We're going to use exactly the same rules. Find the longest chain, find your side chain, identify your functional group, and. So I can see that there it's on the second one. So this will be 1, 2, 3, 4. So my longest chain is 4. 4 carbons is but. And I can see that on the second carbon, there's a functional group that I can identify there. And I can see that when I've got a C attached to a double bond O, which is between 2 other carbons, that is therefore then a ketone. So there, let's just put everything together. So this will be, my longest chain is but, so it's butane. On the second carbon, remember there's a ketone, and the name ending for a ketone is -one, and that was for 2 marks. You could have said 2-butanone if you want, or butane-2-on, it's exactly the same thing. And then number 2.2, it says compound D is a gas used in cigarette lighters. To which homologous series does compound D belong to? Let's just move up to compound number D. I see that it's butane. And remember, if butane only has got single chains, no double bonds, and so forth, so that belongs to the alkane family. That's the functional group in which it will belong. This will be alkane. This you cannot fail. Like I always tell my kids, you cannot fail because you are lazy to read. And unfortunately, chemistry is one of those subjects where you actually need to read, especially all this theory that goes along. So let's look at the next one. It says we must write down the structural formula as well as the IUPAC name of the structural isomer of compound number D. I just want to break this down a little bit. Remember, when we talk about isomers, remember the number of carbons don't change, the number of hydrogens don't change. However, the name or the way the structure actually looks therefore changes. You guys tend to confuse functional isomers, structural isomers, chain isomers. So be very careful. When the examiner is asking for a structural isomer, you know exactly what's going on. When they're talking about a functional isomer, meaning that the functional group is in question, therefore you know exactly what's going on as well as the chain and so forth. So let's look at what number D is, and that is for 4 marks. Just go all the way up. Say we've got number D there. We need to find the structural isomer. So I can see that already I've got 4. So I'm going to do it, I'm going to first draw butane with the structural formula of it, and then I'm going to do the isomer of it. And what's nice is actually, something that you must keep in mind, when you talk about butane, there's only one structural isomer. I mean, there's only 4, and you can only move the carbons as far as possible. So there's only 1. So let's draw the butane first. So we will have butane. If you are struggling with isomers, this is what I would do. Let's draw the butane. But is 4 C's like this. Remember, there's no hydrogen, there's no double bonds, triple bonds, or anything. It belongs to the alkane family. There we are. And there's my butane. Now I must look for an isomer. So I'm going to show you guys how I'm going to do this one. I'm going to move this C and I'm going to put it in the middle. So I'm going to say 1, 2, 3, and I'm going to put it there as a side chain. And there's that C with all its hydrogens. And remember, don't forget your hydrogens. Some of you guys just draw the lines. We're talking about organic compounds here. And there we are. If you can count, the number of hydrogens remains the same, the number of carbons remain the same. And exactly as here, the number of hydrogens hadn't changed, and the number of carbons also didn't change. However, it is an isomer, meaning that the name will not be butane anymore. It'll be something else. So let's see. Let's count. I'm going to say 1, 2, 3. So on the second carbon, I'm going to have a branch, which is methyl. So let me just write it here. So on the second carbon, remember there's a hyphen between a number and a name. One carbon is methyl. Methyl. 3 carbons as prop. And there's only single chain. So this is 2-methyl propane. That's 2-methyl propane. Just want to elaborate on this one quickly. Had I, for argument's sake, said I'm going to take this C in question and I'm going to bring it to the end. 1, 2, 3. I move this C here. And I say, no, I'm going to draw a structural isomer, but I'm going to put it to the end, and then I move it here. Can you still see that this is butane and this is butane? So that's why butane only has one isomer. So always keep that in mind. And what I've actually seen, if you go through most of the question papers, the examiner loves asking that question. And then we've also given it a name. So the examiner wanted to see if you know that butane has an isomer, you know how to draw the structural formula, as well as given the IUPAC name of that molecule. Let's look at the next one. Now we are asked in question 2.2.3, is the isomer in question 2.2.2 a chain isomer? Is it a positional isomer? Or is it a functional isomer? So now let's see, let's go back here. As you can see, this was an alkane. I still stayed with alkane. I didn't have any double bonds or triple bonds on this side, and so forth. So what happened is it's just the chain. The chain just moved. Instead of putting the carbons next to each other in a straight line and making it 4 carbons next to each other, I only just branched the 1 carbon there. However, nothing else changed. So this will therefore then be a chain isomer. This will be a chain isomer. And this is easy marks, really, really easy marks. You cannot fail this. Question number 2.3. It says compound D reacts with bromine. Now, remember when we do this, so when we have different reactions in organic chemistry, we talk about halogenation, hydrogenation, and so forth. Now, it does get a little confusing. So if you are getting a little bit confused with it or you do forget your theory, always draw yourself a structure. The thing with chemistry is it's so abstract that we cannot see it with our naked mind, right? But if you do put a picture in front of yourself, it actually comes back. So I'm going to do it the long way with you. So compound D reacts with bromine, which is Br2, to form 2-bromobutane. We must write down the following. Now, the first thing, they want the homologous series to which 2-bromobutane will belong. So remember, with the butane, I'm just going to have 1 bromine on the second carbon that is attached to it. Anything either than a hydrogen or an oxygen that's actually attached to the carbons, we can therefore say it is then a haloalkane. It's a haloalkane. They can add anything. You can put fluorine, chlorine, and so forth. If you are getting stuck with that one, I would then suggest that you draw it down. I must also write down the type of reaction that takes place. Now remember, for 2-bromobutane, because I didn't break or form any double or triple bonds, I just had Br2 that I broke into Br, and I formed HBr in the one, and the one got attached to where the other hydrogen was sitting, bringing in Markovnikov and Zaitsev's rule. And therefore, this only means this is just a substitution reaction. Nothing was eliminated and nothing was removed. So it's just a substitution reaction. Like in football, you take out the one player, you bring in the other player. So the type of reaction that takes place for 1 mark in this question was for substitution. It's a substitution reaction. You know, just for argument's sake, I've seen exam question papers where they ask you, what is this, besides except substitution, what is another name for the reaction that takes place with bromine? So sometimes the examiner doesn't want substitution, but they're looking for bromination. This is exactly the same thing. So sometimes they can be, what type of reaction takes place? You can say either or, but they can be specific. Except substitution, what do we call the reaction with bromine? Then that will therefore be bromination. And that is therefore how I attacked this organic chemistry. Remember, the only way to pass organic chemistry is to practice and to read. Okay, and I think that's it for this question, and I'll see you after the ad break.
No one ever asks why we do the weird things we do. Like, why once is never enough. Or doing 2 trips is just one too many. Why do we, before we use these, or say 5 when we mean 20, why do we have second thoughts? And think that lift buttons make them go faster? Why don't we walk there? Cross our fingers, touch wood, and struggle to hide our true feelings. At Liberty, we want to know all the weird and wonderful things that make us human, because human beings, being human, are what we make financial solutions for. Liberty, in it with you.
Did you know that butterflies taste with their feet? Butterflies' taste sensors are situated at the bottom of their feet, so they taste their food by standing on it. They do not have mouths, so they can't bite or chew. Instead, they have a long straw-like part called a proboscis to drink nectar and juices from plants.
Welcome back from after the ad break. You're still tuned into Tenfold Live, and I am Thobile. Thank you so much for watching the show. Just sending out tons and tons of love once again to Liberty. Thank you so much for sponsoring the show, and thank you so much for actually giving us the opportunity and this platform to help the class of 2021. We're nearing the end of the year, and all preparations have actually been going really, really well. And another thing, grade 12s, if you haven't done it yet, please do download the Tenfold Education app. It is an app filled with tons and tons of past papers, not only for physical sciences, but also for maths, for life sciences, and all other subjects. So please do tune in there, use it, because now you've written the prelims, and now you can see where your weaknesses are and what you actually still need to be preparing. And if you're wondering what questions we're doing and you'd like to join in the fun, please do send a hi to the WhatsApp number on the screen. And therefore, you shall join in the fun with whatever we're doing in today's show. Today, we are doing paper number 2. On another platform where we're actually fun, active, and alive is on YouTube. And there you can follow us, and we are therefore Mindset Learn. So without wasting any more time, before the ad break, we did a question which was all about organic chemistry. And I remember organic chemistry is actually the foundation of paper number 2, because most of the paper actually counts out of organic chemistry, and you need to understand all the fundamentals. So now we're branching into a little bit of stoichiometry. And now a little bit something different with stoichiometry is that the foundation for stoichiometry is in grade 11. So if your grade 11 was a bit wonk, I would therefore take my textbook for grade 11 and then just go through everything. Remember, what you did in grade 11 is what they bring in grade 12. And they just spice it up here and there, but it's actually almost exactly the same. So remember, foundation for stoichiometry. It is a challenging topic, but I always say to my kids, draw yourself a picture. Even if you have to draw jugs and arrows and everything, it really works fine. So this question is from Bridget, and it's question 6, and we are told here that initially we have 2 grams, and I can see that is already in the correct SI unit, of pure CO2 gas sealed in an empty, and this is the volume, 5 cubic decimeter container. And we are told that it's at 900 degrees Celsius. So they're only given us one thing, actually. So 6.1 says I must calculate the initial concentration of CO2. Now, what are we given? I'm given 2.2, which is the grams. I'm also given the volume of the CO2. In this case, for now, temperature doesn't really matter, but we need to find concentration. So now I know when I'm calculating concentration, there's 2 equations that I could use. So I would say N is equal to small m over big M, but I could also say that C is equal to N over V. I could also say that C is equal to small m over big M multiplied by the volume. So if you are kind of struggling with what formula you need to use or in which dimension you need to go, look at your formula sheet and then see, what do I have and what can I find? Well, what's always nice is only using one formula. It just makes it a little bit more safer. Otherwise, you can use more than one formula to get the answer. Remember to always write the entire answer and only round off your final answer to 2 decimal places. So let's see what we are actually given for this one. I've got the mass, so I can find mass with this one. I've got volume. No, I can't find volume with that one. And here I've got mass, I've got molar mass, and I've got volume. So in this case, I would use number C. However, you could first use this one, get your moles, and then substitute your moles in this equation, and then therefore have equation number 2. So I'm looking for my concentration. I've got my mass. I don't have my molar mass, so this is what we're going to calculate. So I've got CO2. Remember, molar mass is what you find on the periodic table. When we have carbon on the periodic table is 12 plus 2, and oxygen is 16. So I'm going to have 12 plus 2 times that, 16 is 32. So let's see if I can do that by head. So I'm going to get 4 and 4. So that gives me 44 grams per mole. And this is my big M. This is molar mass. However, I'm looking for concentration. So concentration is C is equal to small m, which is the mass in grams, molar mass in grams per mole, and then my volume. Now, guys, remember this. You guys sometimes tend to work out your molar mass on a piece of paper and then you just plug in your answer. You must show the examiner exactly what you're doing. You actually get marks for all these side notes and these side steps that you guys do on the side. So don't calculate your molar mass behind your question paper or anything. Show the examiner, this is what you did, this is what you got, and so forth. Because sometimes when you're marking a question paper, all you see is the answer, then you wonder, where did the 44 come from? So remember, you get a mark for actually showing the examiner what you're doing. By calculating the molar mass, though we do it in grade 10, but you're showing the examiner, you know the difference between an atomic number and a mass number, and you get a mark for that. So let's plug in. So the mass that we are given in this case is 2.2. We have 2,2 grams that we're given. My big M, which is my molar mass, is given to me as 44. And then my volume is given to me as 5 cubic decimeters. So that's 5. Remember, if it was given in centimeters, you would have converted it to cubic decimeters by dividing by 1,000. So let's just plug in that in my calculator. Remember, if you are going to use a calculator for this, always put brackets over your numbers. 2.2 all over 44, 5, and therefore I get 0,01. 0,01. And remember, the SI unit for concentration is mole per cubic decimeter. And that is therefore then my concentration for my CO2. And it is important that you acknowledge that it is initial, because most of the time in stoichiometry, there's a lot of things that happen. They're going to tell you this was added and all that stuff. So now for 6.2, we are told we must give a reason why equilibrium will not be established. Let's just go back to what equilibrium is and what Le Chatelier actually says about equilibrium. Remember, equilibrium is when the forward reaction is equal to the reverse reaction. So the rate of the products being used is equal to the products being reversed. So in this case, why will not equilibrium be reached? Let's see what the statement gave us. They only told us of one thing. So we only have CO2 sealed in a container. So technically what this means is that we only have CO2. Remember, when you're talking about equilibrium, you need to have a forward reaction, you need to have a reverse reaction. So you need to have reactants that make products, or you can have your products turn into reactants back in the opposite direction or in the reverse reaction. In this case, we kind of sort of only have CO2. So equilibrium cannot be established. We're only given one product because it's also just for one mark. So let's see, we can therefore say that for equilibrium, to be established, a forward and a reverse reaction is needed. That's what equilibrium is all about. We talk about a forward and a reverse reaction. So what the examiner is looking for here, they're looking for a forward reaction and a reverse reaction is needed. So you could have said equilibrium will not take place because for it to take place, forward and a reverse reaction is needed. So however you start your sentence, but to show that equilibrium will not be established, you need a forward and a reverse reaction. In this case, we are only given CO2. We are not told that the CO2 evaporates or the CO2 mixes with something else. We just have CO2 sealed in a gas. You know, nothing else is happening. We don't even know if the CO2 is part of the forward reaction or the reverse reaction. And that was therefore then just for one mark. So this was just some properties of equilibrium that we needed to know. So we've got another statement coming along. Let's see what this one says. So now we have calcium carbonate is now added to the CO2 grams of carbon dioxide in a container. Now we've got two things happening. Now I've got one reactant and I've got another reactant. Now they are in the container, and after a while, equilibrium is established at the 900 degrees Celsius according to the following equation. So this is what we have there. The equilibrium constant for this reaction at 900 is 0.0108. So that's the Kc. So the Kc at 900 is what happened. So what I always tell my kids, remember we had a container, and in the container we had CO2. We were told that the CO2 had a mass of 2.2 grams. We calculated the concentration of the CO2 in the container, which we got 0.01 mole dm3. So I'm just showing you the rest of the story. And from that mass, what else were we told? Let me just see. We were told the volume of the container. We were told that this volume is in 5 cubic decimeter dm3. That's the volume of this. And then we are told we add this into that. So now you can see that a reaction is going to take place. So I'm going to just write that, and this is then the calcium carbonate that is happening. Why I like doing this, you'll see with stoichiometry, you usually have to have, you have to use mole ratios to move either from one to the other. Already we know that we can find the moles of the carbon dioxide. We don't really have anything from the calcium carbonate, but using stoichiometry, we can move from one reaction to another because now they are all both added in one container. So let's see what the questions are saying. So number 6.3 says, I must give a reason why this reaction will only reach equilibrium in a sealed container. Now, what I always tell my kids, this is only for 1 marks. Most of our answers for chemistry and physics is in our questions. I want to go back to the statement that we are given. We are told initially 2.2 grams of pure carbon dioxide gas. Now, back to grade 10. We know that we get different phases in grade 10. We get a solid, we get a liquid, we get a gas, right? We also have different, we have using the kinetic molecular theory, we know how they behave. If something is a gas and I put it in an open container, what is going to happen? It's going to go out. You cannot keep a gas in a container and it's not sealed and expect the gas to still be there. It doesn't make sense. That's why when you walk in town and you smell some of the food from the restaurants, it makes you hungry because the gas is evaporating to the atmosphere. That's what gas does. Gas escapes. So the only way that equilibrium can be reached when this reaction is taking place, for it to be established, it needs to be in a sealed container because the gas will evaporate. So give a reason why this reaction will only reach equilibrium in a sealed container, because the other one is a gas. So how can we put this? We can therefore say, in the given reaction, CO2 is a gas. And you want to show the examiner that you read the statement as a gas, and it will escape. It will escape if the container is not sealed. So, if in the given reaction CO2 is a gas and it will escape if the container is not sealed. Just want to go back up here. We are told that the calcium carbonate is a solid, so even though the container is sealed or not, nothing really matters. But the CO2 was given to us as a gas. I can also see that it still says as a gas. So it's very, very crucial. So you could have said anything about CO2 being a gas and it will escape. You could have said the calcium carbonate is a solid, however, the CO2 is a gas. If it's open, we're only going to have the calcium carbonate left in the container anyways if we do not seal it. And remember, equilibrium can only be established then if the container is therefore closed. Let's do the next one. So this one I see is for 7 marks. And it says we must calculate the minimum mass. We must calculate the smallest mass of calcium carbonate solid that must be added to the container to therefore achieve the equilibrium. So remember, every time we have to do this means we have to use either one of two things. I know some educators use the table, like myself. Some educators will use stoichiometry, where they actually break up the components. So I'm going to be using the table in this one. I'm going to go with you step by step. The most important thing when using a table is to make sure that your equation is balanced. In chemistry, you can never actually work with an equation that is not balanced. So let's write down our balanced equation. Let me just look at it here. So this is our balanced equation that we were given. So our equation will be Ca CO3, and we've got CaO, and we've got CO2. So this is what is therefore then important for now. I'm also told, I'm just going to work here on the side piece. Remember, I was told that the Kc for this reaction at 900 degrees is 0,0108. That is the Kc value. This is 0,0108. That's what we were given. So now, in me using the table, I always use initial, I use used, and I say equilibrium. So now, based with this one, I know we're not really sure what we must have, but I know that I need to calculate the minimum mass that needs to therefore be put into this reaction. I just want to add something else. Remember, we were told that the container that it was put in, it was 5 dm3, that was 5 cubic decimeters. So how I always teach my kids, once you have your table and you've written all of that, what I would do is, I would remember, when you have reactants, the reactants get used up during a reaction. But however, the products get made in the reaction, which means that by the product side, we have to use a negative, meaning that it gets less and less and less and less. But the products get more and more and more. Think of it like baking a cake. When you're baking a cake, all the ingredients get less, but the cupcakes get more and more and more. So that's technically what I'm going to do here. So I've got my left-hand side and I've got my right-hand side. And now I'm just going to plug in everything that I am therefore given. I am told, though, let me see, for CO2, we need to find the moles first. So I just want to go back up here. Remember, the initial question that we had, we were given the mass in grams. And I used this equation here to find my moles. So I'm going to have to use these grams again to find the moles of the CO2. If you had actually used in question 6.1, you've used this formula here to find the moles, then you could have just used that answer. But in this case, I didn't. So we're going to have to start there. Let me just go down. Let's just first find the moles. Remember, show the examiner all your little footnotes on what you're getting. So I'm going to find the moles of CO2 because that's what I was given. I know that the formula is N is equal to M over big M. I was told that the mass that we are given is 2.2. And for CO2, remember it's 12 plus 2 into 16. That is the molar mass. So I'll get 2.2 all over 44 grams per mole. So let's see how many moles that is. They did ask us to find the concentration, not the moles. So therefore, that's why I'm doing this, because I need to put the moles in the standard table. So I get 0.05 moles. And this is of CO2. So this means that for this reaction, they did tell us initially we were given 2.2 grams, which is 0.05 moles of this. Now remember, I didn't have anything of that. I didn't have any of that. Also remember that this will get used up, but that will therefore be made, right? Because this is my reactants on this side. This is therefore then my products. So now this is just basic mathematics. So what I'm going to say here, I don't know, like for here, with the CO2, I don't know what actually happened. So I'm going to just put an X there. It is a ratio of 1 is to 1 is to 1. So meaning that here, I'm going to just have X and X. So for example, hypothetically speaking, had we had a 2x somewhere there, I was going to put a 2x because it's twice that of the mole. In this case, it's just a ratio of 1 to 1, so I leave exactly like that. So now we need to find the minimum mass. So I want to show you guys the trick with this one. They are looking for the minimum mass of CaCO3, but we only have information on CO2. This means I need to find the moles of CO2 first, and then I can use stoichiometry to find the moles of calcium carbonate using stoichiometry. So that's exactly what I'm going to do. So now I've established that initially this is what I have. I don't really know how much was made, but now I'm going to find out what I had at equilibrium. So remember, this was being made. It is product. So 0.05 plus X will give me 0.05 plus X. You just leave it exactly as it is. Remember, at equilibrium, we do use concentration, and concentration is C is equal to N over V. So I'm going to say my N's, I'm going to keep it as 0.05 plus X, and we were told that all of this was in a volume of 5 cubic decimeter. So I'm going to leave that as a 5. I am also told, or I do have the concentration that I have, or that I was given. Where did I write that now? Let me just go back up. We do have the concentration, which we calculated in the first one, which was 0.01. So that's what we have there. So we have the concentration of 0.01. 0.01. However, I'm not going to use that step because remember, this is Kc, and we are given the Kc value over there. So this is one way of looking at it. But the way that I'm going to use, because I know that at equilibrium, I'm just going to use that and I'm going to plug that in as it is. So I'm not going to include my concentration. I'm just going to find my Kc value. Let me move here. So therefore, I'm going to say my Kc is equal to the concentration of CO2. Remember, they did say it was in a container at 900 degrees Celsius. The Kc value for this was given as 0.0108, and that Kc value is what I got there. It was initially given to us. The concentration that I have, I did find the concentration in the previous equation, but I know that now that there's calcium carbonate and all of that, things kind of change a little bit. So I'm not going to use that concentration. I'm just going to use the ratio of the concentration I find from my table and plug it in the Kc so that I can find my value. So the concentration, I'm just going to put it exactly as it is, which will give me 0.05 plus X all over 5. And then the rest of this is therefore then just mathematics. I'm going to do it like this because remember, it is a mole ratio of 1:1. So I don't really have to work out so many things because whatever the moles is of the calcium of carbon dioxide will also be the mole ratio of the calcium carbonate. So therefore, I'm just saying the Kc is equal to the concentration of the CO2, and I'm just going to plug it in exactly as it is. Now, this is just mathematics. How do I solve this? Remember, if I've got a fraction on this side and a number, you have to put the number over 1, and then before we cross multiply. So 0.05 plus X, I get 0.05 plus X. and then I multiply these two together. I hope the grade 9s are watching, because they were also doing this where they have to solve for x recently. 0,0108, close bracket, and that gives me 5, multiply that by 5, and therefore I get 0,045, 0,054. There we are. Then I still need to solve for x. Remember, I'm going to have to transpose this to the other side. I'm going to leave x by itself. If any number, it doesn't really jump the equation sign, but if it jumps the equation sign, the sign will change. So I'm going to have 0,054 minus 0,05. So x is equal to, and I'm just going to plug this in my calculator as it is, minus 0,05. And therefore, this is what I'm going to get. So I get 0,004. I get 0,004. Let me just double check if there's another 0 there. Yes, there's 2 zeros. 0,4. And that is now the moles of what I was first finding of CO2. This is the moles of CO2 since it's the X of CO2. But now, remember, I just found the moles of CO2. I'm not done yet. It is for 7 marks. So now I must use stoichiometry and mole ratios now to move to the other way around. So now this is what I'm going to do now. I just want to move. Let me take all of this off. Hopefully everyone wrote it down. So I'm going to start working from here now. So with what I found now, I found x as 0,004. But now these are the moles of the CO2 that I was given. Now remember, I had a reaction where I had calcium carbonate with CaCO3. And this is the reaction that I was given. Now the stoichiometry comes in. So this is technically a mixture of Le Chatelier's principle and the Kc, as well as some stoichiometry. So it's a mole ratio of 1:1. So I can therefore say moles of CO2 to moles of CaCO3. Now, just to elaborate on this again, I am doing this step because I want to show the examiner that this is an equal mole ratio of 1:1. Don't just jump into the equation and then just plug everything in. You need to show the examiner that you went to the equation and actually saw that it's a mole ratio of 1:1. We did find the moles of this one, which was from the equation, we have a mole ratio of 1:1. The mole ratio of CO2 we found as 0,004. That is x, which is unknown. More mathematics. 1 times 0,04 will give me 0,004. And 1 times x will give me x. So therefore, the x will also be 0,004. Okay, let me just move there. So it means that the moles of the CaCO3 is also equal to 0,004 moles. But we're not done, my darlings. The question said the minimum mass. We needed the minimum mass of CaCO3 that was needed. Now, more stoichiometry. Now I've got the moles, now I need to work backwards and just find the mass. So this is a formula that I can use. So I can therefore say N is equal to small m over big M. I have the moles, I'm looking for the mass. Remember, mass is what we have in grams. I'm going to solve for M. I'm going to say M is equal to small n multiplied by my molar mass. So you can do it all at once or do it on the sideline. I'm going to say CaCO3, which is calcium carbonate. I'm going to find my molar mass. Calcium has got a mass of 40. This is what I find on my periodic table. Once again, remember, you need to show the examiner that you know the difference between an atomic number and molar mass. So you have to don't work in somewhere else and then plug it in. Show everything as you're working along. So I'm going to show mine on the side, and then I'm definitely going to continue. So calcium on my periodic table is 40 plus. Carbon on my periodic table is 12 plus. Oxygen, there's 3 oxygens. Remember, you always read the number at the end of the alphabet and not in front. That just means molecules. So I've got 3 oxygens. And oxygen on the periodic table is therefore 16. So let's work this one out. I just want to say 3 times 16. I get 48. Let me just work that one out. I'm going to say 40 plus 12 plus 38. Let's work this one. Now I'm just going to put everything exactly as it is. Ooh, I said 38 instead of 48. There we are. So I get 48. So I get 48, and I must just add 12, and I must add 40. And therefore, I get 100. So my molar mass is 100. Big M is grams per mole. So that's my big M. So I found my moles. Remember, I used the mole ratios. I did find my moles of carbon dioxide, though. So I'm going to say 0,004. And my big M is therefore 100, because they did say the mass. So I'm going to take that answer that I'm given, multiplied by 0,004, and that will therefore give me the grams that's needed, and therefore I get 0,4 grams. So this is 0,4 grams, and this is the grams of CaCO3 that was actually needed. I just want to go back to this one here. We were just told that this was therefore sealed in this container. So going back to grade 11, usually they would tell you so much of this is used, how much of this is needed when we do limiting and access reactants. This is actually something similar to that one. You needed to find the moles of the one and then plug it into the other one to just find the moles of the next one. So let's just go through this one again. This was quite this was a question and a half. So we needed to find the minimum mass of the CaCO3 that must be added. However, the most information that we had was on our CO2. We were given the mass, we found the concentration, we also needed the volume. And then we were told that initially we had the 0,05 moles into the container that was sealed in. Then I had to use the table. I used the initial, use, and equilibrium. Some people use the I start and so forth, or the ICU table and so forth. So after the ICU table, then I had to find X, because for my CO2, that's all the information that was given. And then what I did there, after I found my X, I was given my Kc value, then I just solved for X, and then I used my mole ratios. This is what we have here. After I solved for X, I used my mole ratios between the two. Remember, you always look at the number in front. Make sure that everything is balanced, my darlings. If it's not balanced, it's not the correct chemical equation. You want to show the examiner that you know exactly how to balance a chemical equation. I used the mole ratio, solved for X, which means that the moles of the calcium carbonate was exactly the same as the moles of CO2, which was 0,004. The question did say the minimum mass. You know, sometimes they want to spice it up and say concentration. So after you found the moles, you then would have found the concentration. In this case, they just wanted the mass. I plugged everything in, and then I got the 0,04 grams. So this was a mouthful and a half. It was a nice question, though, but a little bit tricky. So for 6.5, it says, how will each of the following changes affect the amount of CO2? Now remember, every time we talk about equilibrium, it's all about Le Chatelier, and Le Chatelier says that if the system is disturbed, it will shift in such a way as to counter what is happening. So if you're adding more and more and more, the system says, no, get rid. If you're holding on to something, the system says, no, please take out, and so forth. So every time when they say how will this be affected, whether it increases, whether it decreases, whether it remains the same, always go back to Le Chatelier's principle and what Le Chatelier says on how the system will actually be affected. So now here we are told we must write down only increases, decreases, or remains the same. So let's see what we're given. For 6.5.1, I am told if we were to add more CaCO3, calcium carbonate, if we were to add more of the calcium carbonate, what will happen? Let's just go back here to our reaction that we were given. So how will the system be affected if we added more of, so we're adding more and more and more of this. Remember, the temperature didn't change, right? So how will that then be affected? How will it affect the amount of CO2? It will actually just remain the same. It remains the same. It remains the same. And then let's look at the next one. If the pressure is increased, so if we increase the pressure, remember increasing the pressure means that you decrease the volume. So if you increase the pressure of something, you make the volume much more smaller. So how will that affect the amount of CO2 if the pressure is increased? It means that it will decrease. It will decrease. Remember, when we talk about Le Chatelier and equilibrium, there's a difference between pressure, there's a difference with temperature as well as concentration. Let's look at our last question. It is found that the equilibrium constant, Kc, for this reaction is now 2.6. Remember, initially it was the 0,0108. Now it's 2.6 times 10 to the negative 6. And the temperature decreased. There was a decrease in temperature. Remember, initially the temperature was 900 degrees Celsius. Now they're asking us, is this reaction exothermic or is the reaction endothermic? Now they want to know, fully explain how you arrived to your answer. There was a decrease in temperature from 900 to 700. This means it is endothermic. Endothermic. So the temperature, this reaction is holding heat in. And now remember, how do I know whether it's endothermic or exothermic? The Kc is 26 times 10 to the negative 6. So what does this tell us? That a Kc decrease, there's a Kc decrease at low temperature. That is our first point. Temperature, there's just not one other E. And then the next one, the reverse reaction is favored. There was a decrease in temperature favoring the reverse reaction. The reverse reaction is favored. And a decrease in temperature favors the exothermic. A decrease in temperature favors exothermic. Favors the exothermic. Thermic, there we are. And that is the last bit of the question. Thank you so much for tuning in, and I will therefore see you next week.